Our next speaker is Stephen Cowley. Stephen is a colleague of mine at KDAB. He's the item views maintainer, long-time contributor to Qt. But today we'll talk about a totally different topic, about introspection, QMetaType, QVariant, QMetaObject. So please, an applause for Mr. Stephen Cowley.
Thanks very much. Everybody can hear me all around the room? I'm seeing some nodding. That's good. So my talk is all about type introspection and type unsafety in Qt. This is a talk that I gave last week as well at a different conference, where the conference was all about C++ and mostly C++ 11 and a lot of the new features in there. And a lot of the stuff that is in there is things like user-defined literals, variadic templates, and new library features as well, which are all about getting more compile time safety, especially user-defined literals. But this is a move in the opposite direction, a move towards type unsafety, and also a new sort of feature of introspection, or observing other classes in the same program. A little bit about me before we get into all of that. My C++ background is mostly Qt. I've been using Qt for a long time. I started contributing to KDE about 5 years ago, but I've been contributing to Qt mostly in the item models and the item views sections of Qt for a number of years as soon as they opened contribution. And also I've been doing a lot of stuff here and there inside of Qt 5. I've also been maintaining the CMake files that we have in Qt 5 now, just to give you the CMake integration that you want with Qt 5. And I've also been contributing to CMake itself. And that's a very different kind of C++ compared to Qt. I'm also interested in Clang and Clang tooling. I wrote an automated porting tool to help you port some of the boring parts from Qt 4 to Qt 5. There's a lot of boring stuff that you just have to do. So I wrote a little tool to automate that. I am Irish, but I've been living in Berlin now for the last 3 years when I moved here. So when we're talking about programming languages, we don't just talk about C++. We are also interested in other languages, either to glue together our C++ programs or to allow users to extend them. So often you'll have people extending their C++ programs with Python and Ruby, or they want users to be able to write their own extensions in those languages, just like you can extend Excel with VBA, etc. So mostly we're interested in the C++ language. Bjorn Stroustrup also always says that C++ OX is like a brand new language as well, mostly because of the compile time features that it has. But if what I've seen is anything to go by, C++ 1Y is also going to be quite a new looking language. I started looking through the papers that they're currently discussing. They want to have a new standard out, as has been said before by other people, by 2014, and another one in 2017. So some of the papers that they have out, there's 7 different papers which are all related to type introspection and type unsafety. So some of them are rich pointers. That's a new language feature that they're discussing. There's also the ANI library proposal. That is the Boost ANI library proposed for C++ standardization. It works very similarly to how QVariant works, but that's up for as a proposal. There's also several papers just on the concept of what we want to achieve with this stuff and what's the motivation. This type name strings for C++ is a good one. So there's other people thinking about this same stuff as well, and it's a good idea to have a look at what Qt is doing and see where C++ wants to go as well. So the motivation for type 1 safety and for object introspection, largely it's language bindings. There's a lot of KDE applications which the user is able to extend using Python scripts or Ruby scripts and JavaScript. Also, QML is essentially just a language binding. It's a lot of classes implemented in C++ and using a JavaScript engine so that you can write your own C++ classes and use them in the JavaScript environment. So that's essentially a language binding. There's also domain-specific languages which you might want to implement yourself for your own use case. That's a reasonably common thing to want to do. That's where you invent your own language to achieve some goal. We'll look a little bit about DSLs later. In terms of introspection and reflection, one of the things that's useful for is tooling. We've got Gamma Ray downstairs at the KDAB booth. I'm sure some of you have seen that. There's also Squish. Uses a lot of these introspection features so that at runtime you can see what's going on with your application or have a test script interact with it itself. So in order to do that, you need some infrastructure to make it possible. Another thing is the unit test. The Qt unit test framework, QtDD12, also is based on this whole type introspection, or uses it at least, to write unit tests. So common languages people use to integrate with C++, Python, Ruby, and JavaScript. And you think, what is the main problem that you're going to encounter in terms of attempting to bind these languages to your C++ application? Of course, the biggest difference is C++ does type checking at compile time, and all of these languages do type checking at runtime only. In Python, almost everything is an object. Even an object type is itself an object of type. And they close the loop by saying that type is an object of type as well. In JavaScript, a lot of things are strings. So what you end up needing in your language binding framework is type to string conversions. That's what you need a lot of the time. You also need a way to move types through API boundaries. That means that if you implement your own C++ class, your Python bindings don't necessarily need to know everything about that class in order to use it. The same thing, of course, a lot of you are familiar with QML by now, but it works in much the same way. When you want to extend QML with your own classes, you're able to do that without modifying the QML engine itself. And in order to do that, you need to have a way to get your class in there through that API boundary. We also want to be able to find the capabilities of types. So given an object of a certain type, what methods does it have? If I am evaluating my Python or JavaScript script and I attempt to call a method, is that even legal? That's a check that needs to be done at runtime by the language binding implementation itself. And that's also a part of introspection. So back to one of these papers that I was looking at in the C++ language committee. Type name strings for C++. He says, string-based identification enables C++ to cover more use cases. That is, language bindings, creating mock unit test frameworks, etc. And he says that the problems around that are currently impossible to solve without crude external scaffolding. So let's have a look at some crude external scaffolding. In Qt, we've got these classes which we use at runtime in order to do type or C++ type to string comparison and everything like that, and introspection. And also, of course, the QVariant helps us get through the API boundary. that stuff is implemented by using some compile time features of C++. So there's a lot of macros involved there, a lot of template implementations. By Qt5 by now we're doing a lot of more complicated template magic in this kind of scaffolding, more than we've done before. And there's a third time which is providing features for us, which I'll get back to you later. First of all, looking at the Qt classes themselves, we'll look at QVariant and QMetaType. QVariant, first of all, is a wrapper around a C++ union. So C++ union is a special construct in the C++ language where we can give it a number of types and names, of course, and C++ will ensure that any type, any one of those types will fit into this data member. So we can put it in there and we can take it back out. Of course, the long and the void star are different sizes, you know, especially on 32-bit versus 64-bit machines. But the union ensures that there's always enough memory that we can put any of those types in and take it back out. So, salt and pepper. You'll see these things on tables across Europe and America at least. But the thing about these salt and pepper shakers is that the types they contain is defined at build time or manufacture time of the shaker. It's got an S engraved in it, so you know that one's going to contain the salt. However, like I said, I moved here from Ireland, and where I come from, it seems things are a little bit different. So considering this one on the left, who thinks that one contains salt? Some of you. Last week it was about half the room. Who thinks it contains pepper? Okay, that's most of you. I'm sure most of you are German. In Ireland we put salt in the one with one hole. In Germany they put pepper in the one with one hole. So that I like these localization issues. I come across them all the time in language and in, you know, at restaurants. I like to collect them and write about them and talk about them. So this one is just like a QVariant. The one which had S and P engraved on it was not like a QVariant because the type that it was holding was defined at build and manufacture time of the thing. With this one, you give me that one on the left, and I don't automatically know what it contains. So inside of that QVariant, apart from just wrapping a union, it also has an integer type. This is actually a meta type. This is a number which corresponds to a unique C++ type. So assuming that I've put something into the QVariant, there's also an integer telling me what exactly is in there so that I can take it back out. The way to use it, of course, there's some implicit constructors on the QVariant so that I can simply assign values to a QVariant. That works with any C++ built-in type and also with any Qt core built-in type. So there's constructors to help you out there. There's also this static method from value on the QVariant class, and that's what you use with almost everything else, including your own subclasses and your own user-defined types which you want to put into a QVariant. It is a template method, but usually you don't specify the template argument because that can be inferred by C++ by the actual parameter that you pass to the method. I'm just showing it here to emphasize that that is a template type. We'll be looking into those later anyway. Once we have a QVariant, we are able to extract what is in there, either with a convenience method to int, or by using the value template method. So in that case, we do always need to specify what type we want to take out of there. So looking at the implementation of value and looking at what it's doing, it does two things. first thing it does is it ensures that there is a item in the QMetaType database which is able to convert from a C++ type to an integer. So that's the ID is the metatype. This will create a new metatype for a C++ type that hasn't been used before in that way, or if it has been used already, it will return the existing type from the last time. After that, it uses a private constructor on the QVariant in order to construct one. This one goes into the type field on the QVariant, and this, of course, goes into the data field to populate the ABI that we just looked at. The value method then, that's the one where we take something out of the QVariant. It also needs to ensure that the metatype database is already populated. So it calls the same method that fromValue calls. And then afterwards it checks the type to see if what I'm actually containing is what the metatype for the C++ type. It checks if they're the same. If it is, it returns the thing that the QVariant is containing. Otherwise, it returns a default constructed type. So that means that anything that we want to put into a QVariant must be default constructible. That's a specific term in C++ that means some things. So for user-defined types, how do we get those into a QVariant? I mentioned before that QVariant has built-in support for all of the Qt types, but for your own stuff, if you want to put it in there, you need to use this QDeclareMetaType macro. And after you've done that, you're able to use fromValue and value just like with any other type. If you don't use that macro, in Qt4 at least, if you don't use that macro, then these lines will not compile. Also, of course, these lines might be in two completely different translation units. So you'd be able to pass the QVariant through a QML engine or a Python binding, and as long as that didn't try to do anything with it, it would come out the other end and you'd be able to extract the C++ type again from the QVariant. So there's some magic there. QDeclareMetaType, let's look at what it does. So this C++ macro is actually creating a template, a specialization of a template which is part of Qt itself. So if you look into the QMetaType.h header, you'll see a QMetaType ID struct. And now we're going to specialize it with the type that we've just created, the user-defined type. That means anytime we call the static method on this type, QMetaType.id, it'll be calling the one that results from using this macro. So this, in fact, is the method that we've seen before. If I go back a slide, it's the same one that the QVariant API uses to populate the MonType database. So this is how that works. This is why that use of it in the QVariant API implementation actually populates the database. It's because we've used this macro. So the important thing that it does is it also, because this is a macro, we're able to create a string from the C++ type. And that's what this pound sign does. That's a special character in the preprocessor language. So whenever this method is called, the C++ type will be registered with its string representing the C++ type. And what it returns is an integer. That's actually the metatype, which is unique and well-defined for the C++ type. But we have to go deeper. Let's look at QRegisterMetaType now and see what that's doing. So this is this is again a template method. We don't specialize this one, but we just use the implementation which is in Qt. So we get the type name as a string, and we create some destructors and constructors, helpers. So these are the QMetaType delete helper and the QMetaType construct helper are little templates using the C++ type, which give us the constructor and the destructor for whatever type it is. That's needed because at times the QVariant needs to be able to destroy and create new types based on what's already in there. So after that, we populate the actual database. So we register the C++ type, given its string, and the helper methods. And what it returns then is the integer. So that's like, it returns us the next number which hasn't been used yet, just like a database would do with its primary column. So that populates the database, and now we can use it. We use it by using this QMetaType class that has the type name method, which gives us a string for any given metatype, integer. There's also the type method, which gives us the integer type for any given string. So that's already two useful mappings that we have there. So for any QVariant, we can get a string which tells us exactly what type is in there. The other conversion that we can do is, given a C++ type, we can call QRegisterMetaType to get the metatype for that. In the actual implementation of this thing, it's doing caching. So even though this is called QRegisterMetaType, it doesn't register each time. It only registers once, and then afterwards, it's not registering anymore. There is another method called QMetaTypeID, which does the exact same thing. That is, make sure the database is populated for a particular C++ type, and return the metatype ID for that C++ type. So far we've seen some of the things that we wanted to achieve from the outset. The QMetaType class is our API for mapping between metatype IDs and strings. We've also seen how we map between C++ types and metatype IDs. The strings were extracted at compile time as well for each of our metatypes using that QDeclareMetatype macro. And the mappings are defined, populated, and available at runtime. So using those APIs that I've just shown you, any of your classes or any of the Qt language bindings are able to process any of those C++ types. So for introspection, we're interested in using that metatype database with the QObject and the QMetaObject classes. As I said, that's useful for tooling, gamma ray and squish. And of course, now we get to see what the third part of my scaffolding is. Everybody in this room knows it, I'm sure. That's code generation, using mock to generate QMetaObjects and to generate a QMetaCall implementation on QObject subclasses. So given a QObject subclass, this is what you would write. You need to use the QObject macro. That's the marker for mock to know that it's supposed to generate some code for this class. And in this example, what I'm showing and I'm going to talk through is the use of the QProperty macro. So that one expands to nothing in regular C++ code, but it gives a lot of information to mock, which also pre-processes your class definitions. It gives a lot of information to mock about what kind of code it's supposed to be generating. So in this case, I'm defining a property called name, which is a type of QString. The type of it is QString. And I can read that property by calling the name method, which I've got here. It's uninteresting, so I've grayed it out. But I do have an implementation of it somewhere. And so I can use it. Given a complete implementation of the customer class, I can create a new one. And even if all I have is a QObject pointer, I can still call the property method in order to access that property which I've defined here. So this as well, by the way, could be done just in another translation unit, in a translation unit which is not aware of the customer class at all. But QObject allows us to read the property anyway. That, of course, returns me a QVariant, and I can extract that in the usual way. So what does mock generate? If you ever look at the mock files generated by the mock tool, you'll see a lot of confusing stuff, but I'm just going to show you through some of it. And hopefully I won't be too confusing. So one of the first things you'll see for each class is an array of integers called QMetaData followed by the name of the class to make it unique in the entire binary. And what the numbers are is they're actually offsets into a string, which we'll be looking at later, or they're offsets into other parts of itself. So in this one, the class name, I'm saying that the name of the class begins at position 0. And here I'm saying I've got one property, and it begins at position 14 in the string. So just to look at that string to give you some context, this is the next thing that you see in the mock generated code, the QMetaData, meta string data underscore the name of the class. So you'll see a very long string in your own QObject subclasses. And you'll see at position 0, if I start reading this string, I'm going to get the name of the class as a string. So here I've got my properties section of this integer array. Tells me there's one property, and the next integers for it start at position 14. So if you count down here 0, 1, 2, 3, 4, when you get down to 14, you'll be here. This is some new integers. The first one is the name. The next one is the type. The next one is some flags. The flags are things that I haven't talked about before yet, but that's things like, is this type a pointer? Is this type large, so bigger than 64-bit or 32-bit, so bigger than the size of a void pointer, etc. So those kind of QType info flags. So name and type, 17 and 9. Type begins at 9, and if you count from 0 here, when you get to 9, you'll be here. Start reading the string, and you see the type of that thing is QString. So that's how you get that's how everything that uses the mock generated code is able to find out what is the type of that property. Again, if you start reading at 17, you'll start reading here. Name happens to be the name of the property that I defined in the customer class. Here. So of course, when you're using this stuff, you don't care about those integer offsets. All of that is abstracted away for you by classes like the QMeta property, the QMetaObject, QMetaMethods, etc. So this stuff works not only for properties, but also for all the signals and slots, the enums, the flags, and any QClass info that you use as well in your QObject subclass. Another thing that you'll see in the mock generated code is a little piece of code here which populates the static meta object on the customer type. So this is a static QMetaObject which is actually built into the QObject macro. So the QObject macro doesn't expand to nothing in regular C++ code. It expands to define this static meta object on your type, and it also expands to define the QtMeta call. That's a virtual function which is virtual in QObject, and so the signature of it is defined on the customer type, and then the implementation of it is defined by mock. And this is what you compile into your code, so everything works nicely. So just back a slide again. Sorry for all the jumping between slides. Just looking again at what this static meta object actually is. It's populating the struct with the string that I've just been looking at, and also the Qt metadata, so that's all the integer offsets. So first mock generates these things, it calculates where in the string everything's going to be, generates the string, and then populates this static meta object. The other thing that it puts in there is a pointer to the parent meta object. In my case, customer inherited from QObject, but if I was instead inheriting from QWidget, this thing would be a pointer to the QWidget static meta object. And that is useful because that allows us to inherit Q properties and inherit signals and slots and everything. And so at runtime, when Qt is trying to figure out, if I emit this signal, what slot is connected to it, or what slot is it connected to, it's going to look through not only the customer type, but also the QObject type in order to find the slot. So the Qt meta call, like I said, that's a virtual function on QObject, and the QObject macro and mock together work together to define a re-implementation of that virtual method. And what it does is, first of all, it sees if the base class is supposed to handle this stuff. So Qt meta call is an internal method that Qt calls whenever it wants to read a property or find out what signals or slots are available on the object, or to invoke a signal or a slot. So if ever you've looked at a backtrace of a breakpoint from a slot in your code, you will probably have seen Qt meta call in there somewhere. So in this case, what we want to do is we want to call this method in order to read the property. So first of all, we want to see if the base class actually handles that property. If it does, fine, great, we return. Otherwise, we use the implementation generated by mock. The ID here is actually an index into the properties or the signals or the slots on the class, in this case the customer class. So as I've only got one property, it's at position 0. So whenever that method is called with 0, I actually call the C++ method name on this object. So that's how we're mapping from the string read to actually calling a C++ method on our object instance. It's because this code was generated by mock, and because the QMeta property code uses this in order to actually call the method. So now when you're looking at your JavaScript or your Python code, you can probably imagine how it's actually working. So given a customer object, in JavaScript, dot is the delimiter for reading properties. So when I say dot name, the language binding implementation goes through all the code that I've just shown you. It looks up what is the type of the name property, to see if JavaScript can even use that type. It then looks up which of the properties is it. Is it property number 0, number 1, number 2? And then it calls the QtMetaCall implementation in order to actually execute the C++ method name. That's returned, put into the name variable, and you're done. Similar with Python, the language binding implementation itself uses the exact same implementation, the exact same code that I've just been showing you. QML, obviously it's based on JavaScript, but it's not only JavaScript, so they also do the exact same thing in the QML language. That's essentially a domain-specific language, but you can also implement your own domain-specific language. I did that for myself and for anybody else who wants to use it in order to generate some code. This sort of thing is very common in the web world where people want to generate HTML from some set of data, so they need to use a web template system. There's one which I had used called Django based on Python, and I decided to port the domain-specific language that used to Qt. So again, I need to use all that code that I just showed you to access the properties. And I also need to know certain things about the type. Is this type iterable? If it is, then I'm able to loop over it. That's the kind of thing that you can extend with the QMetaType system yourself. It's not built in yet, but I'm hoping to build it into Qt 5.1. And that'll just make implementing your own DSLs really, really easy. It's already a lot easier to implement your own DSLs in Qt 5 compared to Qt 4. One of the reasons for that is there's now a built-in QObject cast which you're able to use through the QVariant API. So how many of you have used QML before? A handful. And you've implemented your own subclasses which you then put into the QML environment, and maybe you had a property on that class which returned a QAbstract item model or some other type derived from QObject but not actually a QObject. And if you try to do that, QML will just choke. It'll say, I don't know how to handle a customer star. So you need to change your property type to QObject star and then everything works. But you also need to make sure that you always put in QObject stars into your QVariant and not customer stars. There was actually a thread on the Qt interest mailing list just this week about exactly that. So it's a problem that people can hit all the time. In Qt 5, that's a much smaller problem. QVariant now allows you to put in a QLabel. So the type of this thing will be a QLabel star. And then later, you can take it out as a QObject, and that will simply just work. It only works for QObject subclasses, though. It won't work for inheritance hierarchies of other C++ types. Only QObject. And of course, once you get the pointer to that thing, you're able again to use the property method to read any property on the type. That gives you a QVariant, and you can use it as a string. So that makes implementing your own DSL so much easier than before. So in this diagram, I've got 3 translation units. The third one is my DSL implementation. The second one is something else, and the first one is your code, essentially. So imagine instead of a QLabel, it's the customer type that we want to put into a QVariant, and we want to return that from some API that'll be handled in some way and then passed to the DSL. And the DSL doesn't need to know about the label type in this case in order to use that QVariant. If you want to, so this is perfectly possible in Qt 4, but if you look down here, in Qt 4 you have to explicitly cast the label to a QObject star when you populate that variant. There's no warning about that. There's no, error. There's nothing. And that's because it's also a completely valid thing to do, in Qt4 to put a QLabel into a QVariant and know that it's not a QObject, and not know that it's a QObject. That's perfectly valid in Qt4. So the user might not be doing that, and they get confusing errors just like people do with QML. But with Qt5, that's no longer an issue. So I'm quite proud of that change. It's one of the things that I did in Qt5. Makes things a lot easier. Another thing that I did in Qt5 was I made it I made it unnecessary to use the QDeclareMetaType macro on certain types of types. So any QObject subclass that you write, you no longer need to use QDeclareMetaType with it in order to get it in and out of a QVariant. Also, any QList or QVector of any type which is itself a metatype, you no longer need to use QDeclareMetaType with that either. Same with smart Qt pointers like the QShared pointer. And of course they can be chained. So if I've got my widget type, I can just put it in there without using QDeclareMetaType. Now in Qt5, I can put a list of ints, a list of my widget star, and also the variant, by the way, knows there that that's a list of things which derive from QObject, so it makes it easier to iterate over them. Similarly, you can put a shared pointer to my widget or a vector of shared pointer of my widget, so you can expand that any depth that you like, which might not be so useful or a good API, but for DSLs, that kind of thing is useful. Also annoying somewhat in Qt is that you often need to use the QRegisterMetaType method. If you've used the QTestLib to write your own unit tests, often what you do is you write data-driven tests. So you use the QFetch macro and you use QTestNewRow and QTestAddColumn. And often you get errors at runtime because the type isn't defined yet. And that's because you haven't used QVariant value or QVariant from value early enough in your program so that the metatype database is actually populated. Recall that when I showed the QVariant value and the QVariant from value implementations, the first thing that they did was populate the metatype database given a C++ type. So if you haven't done that yet at runtime, there's no entry mapping from a string to a C++ type in the metatype database yet. So you'll hit that in unit tests, and you also hit it if you use the QProperty macro with custom types. I've made it so that in most cases you no longer need to use QRegisterMetaType anymore. So if you're reading a property which has a custom type, you don't have to call QRegisterMetaType anymore because mock generates code to do that for you. As part of the QMetaCall implementation, it'll make sure that the MIME-type database is populated. That's something we can only do because we have code generation. That's not something that we can have magic for using macros or templates or the other. So the standard C++ ways to do magic like that. But because we have code generation, we're able to do that. So yeah, this reasonably complicated diagram is just how that works. When we read a property from a QObject, it first queries the QMetaObject to get the property, the QMeta property, which we're trying to read. When we try to read from it, it'll do a type check to see if the type is already in there. If it's not, then it registers the C++ type, reads again, and then everything works. So that's your run through all those Qt features. You saw the runtime features and the runtime APIs that you use. the QVariant and the QMetaType. You saw some of the macros and the template magic that is hidden from you, but which you're actually using in order to make those features work. We saw the runtime registration and how that happens. And I showed you how you can do some type conversions as well using the QVariant, especially in Qt5. So by now we have some time for questions, so if you've got any, stick up your hand and wait for the microphone. At the back.
I've used QProperty quite a lot to make my code more extensible.
Mm-hmm.
So basically I add a property and I don't worry about copying, loading, saving, comparing that property in my object. But there's two limitations that I found pretty annoying, and maybe you know a way around them. The first thing is I would like to add some custom data to each property, like a short description or like something that the user could get if they press F1 in the UI. Is there any way to extend the information that the QProperty macro can hold?
Yes, in theory at least. Nobody has written a patch to do so, but because the QProperty macro expands to nothing in C++ code, we don't have any binary compatibility issues that would come up with that. So extending it with a description component, just like we have the read component, the write component, the notification, the notify component, that will be quite possible. But nobody has tried to do it yet, as far as I know.
Wouldn't that require changes to mock?
It would require changes to mock, yeah. Oh. So I mean, this would be a Qt 5.1 or 5.2 feature.
Nothing that I could do as an application developer, basically. Not easily, at least.
Well, maybe we can think of something. Maybe we can talk about it afterwards.
Okay. Second thing is, when I use property, when I want to use properties, I have to decide, do I use properties or do I have a copyable object? Because properties only work in QObject. Is there any way around this so I can have properties in copyable objects?
No. Yeah, no, there isn't.
Fred, so thanks.
Yeah, sure.
Thank you.
Another question here at the front.
Okay. There we go.
So yeah, the risk of sounding stupid. I was a bit confused by your first customer example where you had a struct. Whether that was stored in the QVariant by value or did it do some allocation and copy?
There is a hidden copy, yeah. There is a hidden copy made. It's something that I took out of the slides, but in the actual...
That copy's on the allocated, is it on the heap or is?
Yeah.
Yeah.
It uses placement new, I think.
Okay.
But so here in this QRegisterMetaType method, it's not only the constructor and the destructor that are activated there. There's also a way to copy the type. Yeah.
Right. Okay.
There's a question at the back.
Could you enlighten a little bit how this new template-based slot and signals feature works?
Sure. I've got a few minutes for that. I think Olivier went through that in detail earlier this afternoon. But we can just look at the source code a little bit. So this, so for those of you who haven't quite encountered it yet, there is a new way of connecting signals to slots in Qt, and it uses function pointers instead of string comparison. So in regular signal slot connections in Qt4, it uses all of the information in the QMetaObject, all of the strings that I pointed out earlier, to do a comparison of the types to see if the connection can actually be made. And look, he just walked in the door. It's the man who implemented this new stuff. So, yeah, this new way works both with C++11 and with C++98. I presume you explained all this earlier. Not this part. Okay. So this, it's rather complicated code. There's variadic templates in there, and all this messy part is just the C++98 implementation of what you have to do if you don't have variadic templates. You have to have multiple specializations with multiple different template types, and all of that kind of thing. But here it's actually able to do type comparisons in the C++ way. Instead of just comparing strings, it knows that a int and a float are similar enough that they can be used in signal slot connections. And I guess I don't really have time to go into it, but maybe you can talk to Olivier or talk to myself later about it. Yeah, I guess that wasn't such a good idea. So, any other question? Suna.
With QVariant, when I've been stuffing enums in them and trying to get them out again, I frequently get my first value of a enum out. Is there a way to get warned when I'm doing something stupid like that? My current workaround is adding a first member named QVariant workaround, and then if I ever encounter that, I know I had done something wrong.
I don't fully understand the issue. It sounds like if you put a enum in there, it doesn't know that it's the enum type, but it thinks that it's an integer. Is that the issue?
Yeah, I'm pretty sure that's the underlying issue.
Yeah. I think Olivier also has some patches around that, which might get into Qt 5.1. But yeah, I don't think that issue is solvable in Qt 4, at least. Yeah, it's a complicated thing because, usually an enum is convertible to an int, and QVariant has an implicit constructor which takes an integer, and that's probably the one that's being invoked, and that's why you're actually populating the QVariant with the 0 there. Any other question? There was Andreas.
Yeah, so there's this feature that you put in a subclass of QObject and get it out as the QObject or the pointers. What prevents you from doing that for all base classes, basically? There's probably
I don't
something.
recall. I think this works with QObjects because we have QObject cast, and that's a safe cast. If I wanted to do that with all C++ types, I would still have to use static cast, but I wouldn't know. Static cast is not a safe cast. If it's not like dynamic cast where if it succeeds, it gives me the actual pointer, but if it's going to fail, it gives me a 0. Same way with QObject cast, but static cast doesn't work that way.
Okay. So can't you use dynamic cast, or is that?
Maybe. Actually, I don't really remember.
Yeah.
But
Okay.
I think that was what the issue was.
Okay. Thanks.
Sure.
I have a question. I have experienced a strange problem in QML that I cannot read the custom dynamic properties in QML. Is it my stupidity, or is it true that only hard-coded properties are exposed to QML?
So I think what you mean is, yeah, dynamic properties.
Yes,
We call those.
dynamic.
Those are properties for which we don't have a use of the QProperty macro, but we just use set property anyway, and it's stored along with the instance. It's true that QML does not allow that.
And isn't it pity?
Technically, I think it would be possible, but because the guys implementing QML want it to be as type safe as possible, they disallowed it. I think I might have filed a bug report about that at some point, and that was the answer that I got. It was a deliberate choice.
Thank you.
Sure.
So, any more questions?
I think that's it.
Well, that's it. Okay.
Well, thank you.
Thank you very much, Stephen.